All right, hello. Camera. Let's get rid of this. No, there we go. All right. Now I just have to find what I did with the worksheet. There we go. Awesome. All right. Well, I hope you guys have had a good weekend. I guess we've sort of had in terms of any class meeting or new extra lecture stuff, kind of had a little bit of a 4-day weekend. So hopefully that was nice and recharging. So what we're going to do now is some examples here for series. And I just realized I never put the problem set up, did I? Or did I? I don't remember. It's been a long day so far for me. Let me just double check that I got it up there. Okay, it is. Awesome. Okay. Sorry, my sleep schedule's gotten all messed up, and I've been up since 5 p.m. yesterday. All right. So we have 2 problems here, but each one has several parts. So there's 10 overall. Hopefully we can get through all of them. But yeah, let's see what we got. So problem 1. Right. So in problem 1, what we have are a bunch of series, and what we want to do is see if, 1, if the series converges, and 2, if it does converge, what does it converge to? All right. So let's go ahead and start with the first one here. So here we have 1/2 plus 1/4 plus 1/8 plus ... Right. Now this one here, I think, is a really neat example because we can make a geometric argument as to what this series should be. All right. Now it does turn out that this is a geometric series. And the way we can see that is by looking at the pattern of the numbers that we're adding up. Right? So if we notice on the bottom here, each time we're adding up a power of 2. 1/2 to the 1, plus 1/2 to the 2, plus 1/2 to the 3rd, and so on. All right? So we really are, we really do have a geometric series here, right? As it stands, right, this looks really nice as a series like this. All right? So this is actually a geometric series. So, of course, we can use our usual plan of attack for this. So for example here, I really need k to start at 0 and not 1. There's a few ways we can try and attack this. In the lecture videos, we did a trick where we added in the k = 0 term and then subtracted it back off. I want to show you another technique we actually have that sometimes can make life a little easier. So here, if I want this to instead start at 0 and go to infinity, I made this number down here 1 smaller than it was before. So the trade-off is I have to make everything else 1 bigger. Right? And now if we look at this, we're going to get the exact same series. Right? So whatever change you make down here, you have to make an equal and opposite change in here. Right? This is a technique we'll talk a little more about later, but this is a technique called reindexing. And then to finish sorting this out, well, I would really like something over k, but here I have this extra k plus, or this extra 1. So this is like 2 times 2 to the k. And at this point, we can say, all right, this is 1/2 times, I'm sure this probably isn't too surprising at this point. You should have 1/2 times 1/2 to the k. Remember, 1 and 1 to the k exact same thing. So as far as geometric series go, this is A, this is R, and here we have that absolute value of R is in fact less than 1. So this series is going to converge to A over 1 minus R. So this is 1/2 over 1/2 is 1. So this series, if I add it up, well, first off, it converges because I found an actual number for it, and this is the sum. So actually, maybe I should write here, this means converges. Right, so it converges, and here's the sum. Now, what is that geometric argument that I mentioned at the beginning of this problem? How do we solve this thing geometrically? Well, what's really going on here, if we think about it, let's say this is a square with side lengths 1 and 1. Okay, so what we're doing is we're sort of saying, all right, the first step is 1/2 here, right? So that's our first part. And then I'm going to take what's left over and I'm going to cut this in half. Now that was 1/4 of the square. I'm going to take what's left here, I'm going to cut this in half. That's 1/8. Right? I'm going to take that, I'm going to cut that in half. That's 1/16. Right? I think you get the idea of what's going to keep going. 1/32, 1/64, and so on. Right? And you can see what eventually has to happen here is we fill in the entire square. Right? Eventually that spirals down and fills in. Right? So that's kind of a neat geometric argument. And there's actually an old cheesy math joke that goes along with this, which is a bunch of mathematicians go into a bar. The first one orders a beer. The second one orders half a beer. The third one orders 1/4 of a beer. The fourth one orders 1/8 of a beer. And then the bartender says, "That's enough. Tired of this?" Pours 2 full beers. Says, "Here you go." Right? So think about that and this example, and hopefully that should make sense. Like I said, it's a cheesy old joke, so you don't have to laugh at it. All right. Okay. But yeah, so this sum here is just 1. Right? Any questions about this one at all? Awesome. All right. Let's look at the next problem here. I'll just go to the next page, I suppose. Sure. Yeah, whatever. Next page it is. Right. So here, k equals 1 to infinity of, let's see, we got 2 over. Here we have 2k plus, or 2k minus 1, 2k plus 1. Right? So this doesn't fit a nice, neat geometric series, so we can't use that pattern on it. So let's see what we can do otherwise, right? The other option we have is to try and create a sequence of partial sums and take the limit of that. So let's start by trying to do a sequence of partial sums. All right, so here, AK is going to be this stuff in bracket, or that we're adding up here. Right? So that's our AK, and now S1 is just going to be the first term. So in this case, it starts at k equals 1, so S1 is A1. Right? Plug in 1, and we're going to get 2 over, this is going to be, 2 minus 1, and 2 plus 1. So this is 2/3. Right? Great. Now let's see what the next thing is. All right, so S2, just to keep the pattern that's going to happen here, this is going to be S1 plus A2. Right? So take the previous sum and add the next term. So we need to plug 2 into this. This is going to be 2 over, this is going to be 4 minus 1 and 4 plus 1. Right, so that's 2/3 plus, let's see, that's 2 over 3 times 5, so 2 over 15. So what is this going to be? This is going to be, let's see, multiply this by 5 over 5, so this is going to be 12 over 15. Which we can simplify, divide top and bottom by 3. So this is going to be 4 over 5. Right? Okay. So, I don't know. I have a guess at what a pattern could be here, but I'm not too sure yet. 2 terms it's really hard to say for sure that this is the pattern. So we should use at least 3. So let's look at S3 here. This is going to be S2 plus A3. Right? So this will be 4/5 plus, that's going to be 2 over 6 minus 1, 6 plus 1. So that's 4/5 plus 2 over, let's say that's 5 times 7, so 35. So we need to multiply top and bottom by 7 here. So that's going to give us 28, so 30 over 35. Right, and we can divide the top and bottom by 5 here to get 6 over 7. All right, so if we look at this, do you see any kind of pattern showing up so far? See if you can come up with any kind of guess as to what's going on here. It might help to look at the tops of these fractions and see how those are changing. Look at the bottoms of these fractions and see how those are changing. Another few seconds to see if you can come up with a guess there. And then we'll do the next term so you can see if you're right. Alright, so this is going to be 6 over 7 plus 2 over 8 minus 1, 8 plus 1, 6 over 7 plus 2 over, that's 7 times 9, so 63. So this is going to be times 9, 56 over 63, which is 8 over 9. So the pattern here, hopefully you can kind of see what it is now. If you look at the tops of these fractions, it's 2, 4, 6, 8. Right? Those are the even numbers in order. If we look at the bottoms of the fractions, it's 3, 5, 7, 9. You can bet the next fraction here is going to be 10 over 11. So, Sn is going to be, the top number is always 2 times this index. And the bottom is always 1 larger than the top. So 2n plus 1. How's that look? And one nice thing here, if you're ever unsure about how your sequence is progressing, you can always, check a few more terms, like make a guess and then say compute S5 and see if your model gets it correct, right? Compute S6, compute as many as you need to try and see if your prediction is actually right, if it's getting the correct terms, right? So now that you have that, now we can say, all right, well, the limit, so this sum here from k equals 1 to infinity of 2 over 2k minus 1, 2k plus 1, this is going to be the limit as n goes to infinity of 2n over 2n plus 1. So interestingly enough, this is actually just 1. So this sum also adds up to 1. Kind of interesting, right? But if you think about what's happening here, right, each time we're kind of 1 away from, like, one part of this fraction away from 1. There's a lot of 1s in that sentence. All right. Any questions there? All right. Awesome. So let's look at the next problem. After this, these are going to get quite a bit simpler. Right? So this one here, this is actually a really interesting type of series. Right? So if we look at this, we have 1 over square root k minus, or k plus 1, minus 1 over square root k plus 3. Right? So we actually get some interesting things with this series, or these type of series. So it has nothing to do with the square root or anything. We'll see in a second here. So if we look at this, it's not a geometric series. It's not any special kind of series that we know. So we're going to use partial sums and look at how that's progressing, right? So AK is this stuff here. This stuff in here. Let's duplicate that so I don't have to rewrite it all. Right, so that's AK there. So S1, I really want that to look like capital S. S1 is just A1 in this case. So we plug that in and we get 1 over square root of 2 minus 1 over square root of 4. I had to think about that for a second. All right, so cool. That's 1 over square root 2 minus 1 over 2, but I'm going to leave it like this. All right, let's look at S2. This is going to be S1 plus A2. All right. Oh, this one's a little more interesting than I thought. Okay, we're still fine here. So let's go ahead and write this down. This is 1 over square root 2 minus 1 over square root 4. And then plus 1 over square root 3 minus 1 over square root of 5. Okay. Can't really do anything with that, can we? That's fine. Let's keep going. And I'm not going to simplify this, and you'll see why. S3, this is S2 plus A3. So we have all this stuff still. 1 over square root of 3 minus 1 over square root of 5. And then let's write down the next thing. What are we going to get? Right, when we plug in 3, we're going to get 1 over square root of 4 minus 1 over square root of 6. Sorry about that. All right, now here's where the important stuff starts to happen. That cancels. So what we get is 1 over square root of 2 plus 1 over square root of 3. And then we have minus 1 over square root of 5 minus 1 over square root of 6. Okay. Let's go on to the next one because it's not really obvious what's happening yet. And I should have made this k plus 2. It would have been a lot quicker. But we'll get by here. All right, so let's do this one. S3 plus A4. So we have all this stuff again. I'm just going to duplicate this. All right, but then when we plug in 4, let's see, we're going to get 1 over square root of 5 minus 1 over square root of 7. So what happens here? Well, this and this cancel. Right? So what are we left with? Well, we're left with 1 over square root of 2 plus 1 over square root of 3, and then minus 1 over square root 6 minus 1 over square root 7. Okay, so there's something interesting going on there. These two are just kind of hanging out, and these other two, they keep canceling out the previous one that was there. Right? Let's do one more just to kind of solidify what's going on there. So S5 is S4 plus A5. So that's all this stuff. Get that? Right? Oh. Oh boy. That's great. Give me 1 second here. This is one thing I really miss about whiteboards is, even though you can't copy and paste on a whiteboard, it doesn't freeze on you. Okay. Fun. All right, give me 1 second. I'm going to mute everything here. Take 2-3 minutes here. Hopefully we can just sort it out. We're back. Computer's back. Let me just see. Cool. Let's see, bring all that stuff back. All right. Sorry about all that. Technology always doing what you want it to, right? Okay. So, where were we? Computing S5. All right, so here's S4. Let's compute S5 now. Here. All right. Okay. When we plug in 5 to this, okay, we're going to get 1 over square root of 6 minus 1 over square root of 8. Right? And again, this first term here is going to cancel with that term there. And so we just have 1 over root 2 plus 1 over root 3 minus 1 over root 7 minus 1 over root 8. Right? So hopefully you can see the pattern that's showing up here, right, in all of these. So Sn, this is going to be 1 over root 2 plus 1 over root 3. Right? Now what is the rest of it? Now, something we do need to be a little careful about is it doesn't apply for n equals 1. Right? It's not true there. Okay? But if we look at these, this one is always 2 bigger than that number. This one is always 3 bigger than that number. Or I should be pointing at this. So this is minus 1 over square root of n plus 2 minus 1 over square root of n plus 3. Right? If you look at it, that's what's happening each time. Right? You compare, it works everywhere from 2 onward. If you look at it carefully, that's what we're getting. Right? So that limit of Sn, so this sum that we have from k equals 1 to infinity of 1 over square root of k plus 1 minus 1 over square root of k plus 3. This is going to be the limit as k goes to infinity. Right, let me point out here again, this is valid for n, so I should use n here as well, n greater than or equal to 2, but that's fine. You know, we can ignore the first term in a sequence. It's not going to have any bearing on the actual limit. Okay. We're taking the limit of this stuff. Hopefully it doesn't freeze this time. Cool. All right, there we go. Now, if you look at this limit here, what's going to happen is this has a constant on top and a function on bottom that's getting larger and larger. So both of these go to 0. So that tells us that the answer is 1 over root 2 plus 1 over root 3. Right? And you can simplify that if you want. I don't think there's too much value in doing so. All right. So there we go. All right, now the stuff's going to get a bit easier than these ones here. So any questions about these? Great. So let's go ahead and continue forward. Let's look at problem 4 here. Right, so in problem 4, we have a sum from k equals 0 to infinity of 1/4 the k. All right, so this is geometric. Right, that's a geometric series with a equals 1, r equals 1/4. Okay, so absolute value of r is less than 1 here, so it's going to converge. Okay. And to see what it converges to, well, it's a over 1 minus r, so that's 1 over 1 minus 1/4. And as you'll find out, this ends up being 4/3. Right, so that series there adds up to thirds. Right? Any questions there? Cool. Let's go on to the next one. 5. Here we're looking at the series from 0 to infinity of minus 9 over 10 to k. Right, so think about that for a second. So what do we have here? We have another geometric series. A, again, is 1 here, because everything is to the kth power. And r is, well, negative 9 over 10. Right? And, well, here we have absolute value of r, which is 9/10, is still less than 1, so this converges. And so we can compute the limit as 1 over 1 minus r. Right, and that, let's see, that's going to be 1 over 19 over 10. So this is 10 over 19. Right, that's what that adds up to. Right. Any questions there, Paul? All right, cool. Let's look at number 6 here. So 6 is the sum from k equals 0 to infinity of 3 times negative pi to the negative k. So I'll give you a second to think about that one and what could be going on here. So any thoughts about this one? Yeah, at all what kind of series this might be or how we might approach it? So this thing here, this is actually also geometric. How? Right, this is a negative k here. So we just need to change it to a positive k. How do we do that? Well, just put the negative on the inside. This. Right. Use some properties of exponents here. Specifically here, we would be using a to the pq is a to the p q. Right? What it means when we multiply exponents. So here, a is 3, r is negative pi to the minus 1, which we could write as minus 1 over pi. And so absolute value of r is in fact less than 1, so this converges. Since that converges, we know this is going to be 3 over 1 minus negative 1 over pi, which, let's see, that's 3 over, this is going to be pi plus 1 over pi, so 3 pi over pi plus 1. And that's what that adds up to. Right. Any questions there? Right. So let's tackle this last problem in problem 1 here. This is k equals 0, infinity. Here we have 4 to the 2k over 12k. Oh, sorry, 12 to the k. Right, so what is going on here? Anything need to be done here? So again, this is a geometric series. And here, I need to pull out the kth power. So when I pull it out, I'm going to get this. Right? And simplify this however you so wish. But inside, we're going to have 4/3 to the k. So again, this is geometric. A is 1. R is 4/3. Now in this case, absolute value of R is bigger than or equal to 1, which means it diverges. In that case, that's it. We can't actually compute any value of this because it's going to diverge. I guess in this case, since all the terms are positive, we could say that this adds up to infinity, but we really don't usually say that. We just say it diverges. So, any questions there? This kind of, if you can get this stuff, this kind of sets the tone for everything else. All right, fantastic. So let's look at problem 2 here. All right, part 1, I have this infinite repeating decimal. And I want to know, well, what is this? Right, what is the fraction? Right, this one's pretty easy. We probably all know that this is 2/3. But how do we show that? Right, so we did something similar. I can't remember the lecture videos. I think we did infinitely repeating 9s and showed that that equals 1. Right? So let's look at this here. What we got to do is just view, each repeating part as another part of a sum. So here we have 0.6 plus 0.06 plus 0.006 plus 0.0006 and so on. Right? That's what's happening here. And if we view it like this, well, this is 6 times 0.1 plus 6 times 0.01 plus 6 times 0.001 plus 6 times 0.0001, and so on. Okay. So again, we're trying to break this down to the most basic pieces. Okay, now here, so this is 0.1 to the 1. Here, this is 0.1 squared. This next one is 0.1 cubed, and so on, right? 0.1 to the 4th. So if we keep following this pattern, we're going to wind up with this. And the whole point is here that this is building a geometric series. K equals 1 to infinity of 6 times 0.1 to the k. Right? Now again here, a geometric series should start at 0 and not 1, so we can do that reindexing trick we talked about. So here I'm going to drop this number by 1, make it a 0. And since I dropped this by 1, I have to raise this one by 1. 6, 0.1 to the k plus 1. But now that doesn't quite look like a geometric series anymore, but that's okay. I can just pull off that extra factor I have. This is 6 times 0.1 times 0.1 to the k. And so really what we have here is the sum from 0 to infinity of, this is now 0.6 times 0.1 to the k. And we can see here, this is a convergent geometric series because, well, the mag r is 0.1. So this is going to be 0.6 over 1 minus 0.1. That's 0.6 over 0.9. And I'll let you go ahead and sort that out, but you should get 2/3 as sort of expected here, right? Any questions about that one? All right. Let's go ahead and look at the next problem. So here we have 0.037, All right, so we got this interesting repeating pattern here that has several digits to it. But again, what we want to do is just take this repeating pattern and write it as a sum of things. So this will be 0.037 plus 0.3 zeros and then a 0.37. And then, not going to fit here probably. All right, let's move this to the next line. Fit. All right, so here we have 0.000000037. Right. So what's going on here is we're getting 37 times 0.001, right? Plus 37 times 0.000001, okay? Plus 37 times 0.0000001. Right? What's going on in each case here is we have 37 times 0.001 to the first power plus 37. If you check this out, this is going to be 0.001 to the second power, okay, plus 37 to the 0.001 third power, and so on. Right, now we're just going to play the same game we did in the last problem. So this is the geometric series. In this case, the easiest way to see this is starting at 1. At 37 0.001 to the kth power. Right? So again, we need to re-index this. So we'll start this at k equals 0 to infinity. And now this bumps up to k plus 1. Again, we drop this by 1, so we have to raise this by 1. And do the same trick as before. And this is going to be 0 to infinity. So I'm going to take out that extra copy of 0.001. And what we get is 0.037 out here. And then 0.001 to the k. Right? So what's going on here? We get a over 1 minus r. So 0.037 over 1 minus 0.001. Right? So this is 0.037 over 0.999. So this is 37 over 999. Right? Pretty neat, right? I think this is pretty neat. Okay. I put the decimal in the wrong spot here. Or maybe I didn't, but I'm going to move it. I think the next problem is a little more enlightening if we look at this as 0.1252525, so on. Right? So maybe I should do this. 0.125 bar. So 0.1252525, so on. Like, this problem is a lot more interesting if we look at it this way. What we would do if we had that 1 as written, you would write it as 1 plus the repeating decimal, figure out what that repeating decimal is, and then just add 1 to it. Right here, it's a little more interesting. We're going to do that same kind of idea that I just mentioned, except now the decimal part gets a little more interesting. Right, when the repeating decimal doesn't start at the very front here, we have a little bit more of an interesting problem on our hands. Right? So here, I'm still going to write, okay, this is 0.1, great, plus 0.025, plus 0.00025, plus 0.0000025, and so on. All right. It is 12:20, so if you do have somewhere to be, please don't feel bad about having to leave. Since I had the tech issues, I probably would have finished this one if I didn't have that, but I'll go ahead and finish it. It should take maybe a minute or two here. But like I said, if you have to go, absolutely feel free. All right. So what do we got to look at here? Right here, I want to look at the fact that this is the part that's going to be the geometric series. This one's just going to come along for the ride. Right, so this is 0.1 plus. All right, so what do we get here? This is give me this. This is 25 times 0.001. This is 25 times 0.123. Right? This is 25, not plus, almost wrote plus, times 0.23456. Right? And so on. So if we look at this in terms of powers, this is 0.1 plus 25. This here is 0.1 to the third. Right? Sometimes it helps to just go back all the way to the 0.1. Right? This is 25 times 0.1 to the fifth, 25 times 0.1 to the seventh, and so on. Okay, so if you look at the pattern that's showing up here, we have 0.1 plus the sum from, sorry, I'm going to use 1 to infinity here. And this is 25 times 0.1. Now think about how this is going to progress. You should see the power up here has to be 2k plus 1, because we have a bunch of odd numbers starting at 3, right, as the powers. Now, hopefully that makes sense. Hopefully. Right? So now we need to do all our readjusting here. So the best thing I think to do here is let's change this k to a 0 first. This is 0.1 plus, we bump this k down by 1, and so we bump this k up by 1. Right, now remember, we're bumping k up by 1. So k replaces with 2k plus 1. Now this is 0.1 plus sum, k equals 1 to infinity. It's 25 times 0.1 to the 2k plus 3. All right. So that's going to give us 0.1 plus, oh, sorry, this, I don't know why I changed back to 0 here. Or sorry, back to 1. It's supposed to be 0. All right, so here, that extra 3, I'm going to split all that off, and that's going to give me 0.025. Right? I'm going to move that decimal over 3 times. And then in here, this 2, I'm going to square this number on the inside, so this gives me 0.01 to the k. Right? And now we can go on with our business here. 0.1 plus a is 0.025 over 1 minus 0.01. Right, so that's 0.1 plus 0.025 over 0.99. Right, so this got a little more interesting now. Here's where we want to change everything to a fraction. So this, the 0.1 is 1 over 10. This one here, I have to multiply the top and the bottom by 1,000. It will be 25 over 990. Right? So multiply this. To give it a common denominator, we multiply by 99 on the first one. And so we get 124 over 990. Pretty interesting number. But that's what that is as a repeating, or sorry, as a fraction. That repeating decimal as a fraction. All right, so sorry for going like 5 minutes over here. Again, if anyone did stick around for all that, thank you. Are there any questions here? All right, fantastic. Well, I hope you, I hope this helped clear up some stuff with the Infinite series. And take a short break, and I'll be back in about 5 minutes for the next class. Right. Go ahead and get back to business here. More problems. Well, good afternoon. So here we're going to start doing a lot of infinite series stuff. That's really going to be the remainder of the class is, looking at various ways to utilize infinite series to study calculus. So what we're really going to do for, I guess, sort of this week is talk about, when does an infinite series converge? We won't usually be able to find the sum, but we'll be interested. Really, we just care, is it a finite number or not? Right? That's really what matters most for us. Sorry. All right. So, problem 1 here. Part 1, I wanted to start off with something a little bit interesting. So 1/2 plus 1/4 plus 1/8 and so on. Okay. So this is pretty basic series here. If you look at the things we're adding up in here, there's a certain pattern to them. Okay? We have 1/2, 1/2 squared, 1/2 cubed. This is really a geometric series. 2 to the 1 plus 1/2 squared plus 1/2 cubed, so on. So this is the series k equals 1 to infinity of 1/2 to the k. Right? That's really what's going on here. Now, about this, to find the sum of a geometric series, we need it to start at 0, not at 1. So we did a technique in the lecture videos where we sort of added in the k equals 0 term, but then subtracted it back off outside, and then, did the arithmetic from there. And that's perfectly fine. That will always work. I want to show you probably a slightly better way to do that. And it's through a technique called reindexing that we'll talk about a bit later, but it actually, I wish I had honestly done this in the lecture video, but, yeah, so it's a bit of a quicker technique here. So what I really want to do is I want to start at k equals 0 and go to infinity. So when I do that, notice here, I've moved this number right here. I've moved it down by 1. In order to compensate for that, in order to make the sum still add up in the same way, I just replace this k with 1 larger. Right? So in the sum here, if I lower this by a certain number, I have to raise all the k's that show up in here by that same number. So like if k were 2 here and I went down to 0, then this would have to be k plus 2. So again, we'll talk some more about reindexing a bit later, but it is a quite useful technique. Now, of course, this isn't quite a geometric series anymore, but that's all right, because we can use properties of exponents to sort this out. So on the bottom here, 2 to the k plus 1, that's just 2 times 2 to the k. And once I know that, I can split this up as 1/2 times 1/2 to the k. Right? And remember, 1 to the k, these are the same thing. Raise 1 to whatever power you want, you're going to get 1. So, sum from k equals 0 to infinity, 1/2, this is really 1/2 to the k. Right here. Right. So, now that we have that, here's our A, here's our R, right? And we know here that the absolute value of R is less than 1, so this is going to converge. So this series is convergent. That's great. And what does it converge to? Remember, a geometric series converges to a over 1 minus r. It's this sort of scalar term over 1 minus the ratio. So this is going to be 1/2 over 1 minus 1/2. Is 1/2 over 1/2? 1. Okay. The series converges to 1. So how can you see that? What's a good way to tell that the series is going to converge to 1? There's actually a geometric argument you can make for this one here. Right? So the geometric argument for this one is sort of like, imagine you have a square, or really any unit you want, I suppose. So it can be a rectangle. It actually doesn't matter what the dimensions are. As long as you think of this thing has one unit of area. So it's like one table's worth of area, whatever you want to do that as. So what is this series here doing? It's saying, all right, well, first I'm going to take half of that table, right? So now I have half of it. And then from the leftover, I'm going to take half of that, right? And then from this leftover, I'm going to take half of that, right? Let me zoom in on now because it's going to get small. From this leftover, I'm going to take half of that. From this leftover, I take half of that. From this one, I do half of this. Right, so each time I'm just taking half of the leftover. But if you kind of imagine what's gonna, happen as you go forward here, you keep cutting in half and in half and in half and in half, and eventually you're gonna fill in that entire table, right? It's gonna take forever, literally, to get that last little speck of it. But, this is a pretty interesting concept here, right? So all these have to add up to 1. And actually, there's some fun fact here with, if you guys have ever heard of like the golden ratio, there's a spiral that sort of goes into here. But that's a topic for a completely different class. But yeah, there's some neat stuff with this series. There's also a really bad old math joke that's gone around for a while, which I'm going to subject you to, which is infinitely many mathematicians walk into a bar, and the first one orders a beer, and the second one orders half a beer, and the third one orders a fourth of a beer, and the fourth one orders an eighth of a beer, and then the bartender's like, that's enough of this, and pours 2 full beers and says, here you go. It's terrible, but I don't know. Every student learning series has to hear this at some point. So, you're welcome. All right. So, terrible joke aside, though. Any question about this one at all? Just straightforward there. All right. So let's look at the next problem. Let's go to the next page here. So part 2. All right. So here we have the series k equals 1 to infinity of 2 over 2k minus 1. 2k plus 1. Right? Excellent. All right. So that's not a geometric series. It's nothing even close to a geometric series. So let's try and, write out what's going on here with partial sums. Right? That's the only other tool we have at this point for finding sums. And, well, there's not really many tools out there for actually computing sums. So, at least easily. All right. So what we're going to do here is say, all right, well, this stuff in here, I don't want all of that. All right, well, whatever. The AKs, the things that we're adding up, let me just pull out what they are. So these are the individual summons of this series, right? This part right here is the AK. We're going to take partial sums of this. So S1 is just going to be A1. So plug in 1 here. It's going to be 2 over 2 minus 1, 2 plus 1. So, end of the day, we're going to get 2/3 here. Cool. Let's do the next one. S2 is going to be, I want to keep the pattern here of saying it's the previous sum plus the next term. So S1 plus the next A. Right? So this is going to be 2/3 plus 2 over, this is going to be 4 minus 1 and 4 plus 1. Okay. So that's 2/3 plus 2 over, that's 3 times 5, so 2 over 15. We combine those together with a common denominator. That's going to give you 12 over 15. Because this is going to be 10 over 15 here, plus the 2 over 15. And let's simplify this so we can divide the top and bottom by 3, and we get 4/5. How's that look so far? So at this point, start thinking about what pattern might be emerging here. See if you can, make any guess as to what's going on. And as you're formulating that, though, go ahead and do the next one, because you can't really, for sure get a pattern just off of 2 numbers. You need at least 3. So let's go ahead and do the third one. S3. That's going to be S2 plus A3. That'll be 4 over 5 plus 2 over, let's see, this is going to be 6 minus 1 and then 6 plus 1. So we have 4/5 plus 2 over, it's going to be 5 times 7, so 35. So we have to multiply here by 7 over 7 to get a common denominator. So that's going to be 30 over 35. Right? If you common denominator this, add them together, that's what you're going to wind up with. And the top and bottom are divisible by 5, so simplify it, and we get 6 over 7. So now that we have 3 numbers here, 3 of the partial sums, think about, what S4 should be. You can even compute it if you want, but I challenge you to think about what it might be, because that's going to help you figure out, well, what should the pattern going on be? So I'll give you a minute to think about that, and then I'll do the computation for S4, and you can see if your guess is right. Give you a little bit to think about what pattern might be going on here. All right. So I'm going to go ahead and compute S4 real quick. 4. S3 plus A4.
8 over 9.
Yep. We'll see here in a second. Let's see, so 8 minus 1. plus 1. 6 over 7. Here we're going to get 2 over 63. So this is going to be 56 over 63, which, if you simplify it, is exactly 8 over 9. Right. So there's a few ways to kind of look at this pattern. The easiest one to see is probably that the top keeps going up by 2 and the bottom keeps going up by 2. Right? So the next term would probably be, well, would be 10 over 11, and then 12 over 13, and so on. Right? So from there, though, we need to formulate, a general SN for this. Right? The question is, well, what should that be? What should the general SN term be? Look at how our numbers are progressing here. Right? Let's start with the numerators, for example. So the numerators are 2, 4, 6, 8. Right? In particular, they're the even numbers in order. And in fact, they're the even number that's always double this index down here. So it's probably not surprising that that should be a 2n on top. And then now, if you look at the denominator as always being 1 larger than the top, you can see it's 2n plus 1. And so that's our general SN term, our partial sum after n terms have been added together. Right? You can also look that the bottom are odd numbers as well, and base your guess off that. So now we have our general term here. So this series, 1 to infinity, 2 over 2k minus 1, 2k plus 1. This has got to be the limit as n goes to infinity of this partial sum here. 2n or 2n plus 1. But now here, now that we have that, there's not really any fancy math going on anymore. This is just a simple limit. Take the ratio of the top and the bottom coefficients, because they both have degree 1. And so this series adds up to 1. So either that limit's going to exist and the series will converge to this number, or this limit won't exist and the series will diverge. Right. So, any questions about this one? All right, awesome. So let's look at the next series here. Next series is a bit of an interesting one, as we'll find out. We have series from k equals 1 to infinity, 1 over square root of k plus 1. I honestly wish I had written 1 over square root of k plus 2, but I didn't. So we're going to do this one. All right. So this isn't geometric. That's probably not too hard to figure out. So what can we even do here? Do we have any hope of computing this? Well, so if we're going to have any hope of computing this, we need to get a sequence of partial sums. So again, remember here, all this stuff is AK. Right. And let's start our adventure with the partial sum here. So S1, if we plug in 1, we're going to get 1 over square root of 2 minus 1 over square root of 4. Yes, 1 over square root 4 simplifies. Let's not do it. Let's go ahead and write down S2. Right, so S2 is going to be S1 plus A2. So this is 1 over square root of 2 minus 1 over square root of 4. And then that's the first part. Plus, when we plug in 2 here, we're going to get 1 over square root of 3 minus 1 over square root of 5. All right, so nothing fantastic has really happened here. All right, let's go to the next one. S3. It's going to be S2 plus A3. So we're going to get all of this. I really don't want to write again. Oh, do this here. Right, so S2 is that, and then plus A3, plus plug in 3 to this contraption up here, we get 1 over square root of 4 minus 1 over square root of 6. Now, at this point, something is happening. What is that something? Well, this 4, 1 over square root 4, and this 1 over square root 4 cancel. Right? So, what we have is 1 over square root of 2 plus 1 over square root of 3 minus 1 over square root of 5 minus 1 over square root of 6. All right. So we're not really worse off than we were for S2. Maybe you can see what's going to be going on here. Maybe not. Let's do another one. Right? If you're having trouble getting the pattern, something that could always help is to try and compute the next one. So S4 is going to be S3 plus A4. So S3 is this stuff. Plus A4 is going to be 1 over square root of 5 minus 1 over square root of 7. Right? And if you look at what happens here, well, this and this cancel now. So we have 1 over square root of 2 plus 1 over square root of 3 minus 1 over square root of 6 minus 1 over square root of 7. This pattern would have showed up a lot quicker if I had used plus 2 instead of plus 3 here, but it's fine. So now we see S4. So you guys kind of seeing what's going to happen now? Let's look at one more. Let's look at S5 and see if, if you can see a potential pattern happening here. See if you can figure out what it is. So S5, which is going to be S4 plus A5. So it's going to be all this stuff. Plus A5, which will be, let's see, 1 over square root of 6 minus 1 over square root of 8. And again, look what happens. The negative and the positive cancel. And we get 1 over root 2 plus 1 over root 3 minus 1 over root 7 minus 1 over root 8. Right, so especially when we look at S2, 3, 4, and 5, well, you can start seeing a pattern that's happening. I'll give you a second here to think about it, and then I'll write down what that pattern is and see if that checks out with what you have. So the general SN term here is going to be 1 over square root of 2 plus 1 over square root of 3. Those parts never go away. And then here, going to be minus 1 over square root of n plus 2 minus 1 over square root n plus 3. That's what you should have. So these two, 1 over root 2, 1 over root 3, they just stick around forever. And if you notice here, we have root 5 and root 6 for S3. So that's 2 and 3 higher. Here we have root 6 and root 7 for S4. Those are 2 and 3 higher than 4. Here we have 7 and 8, which are 2 and 3 higher than 5, and so on. Right. One thing to point out with this pattern, which is kind of interesting, is n has to be at least 2 for this pattern to take hold. Right, this pattern doesn't make sense if n is 1. Actually, wait. Is that true? No, this formula is true if n equals 1, isn't it? Oh, okay. Never mind. I take that back. Sometimes these formula only make sense for like n equals 2 or 3 or something higher. And the first few terms of a sequence, if you remember, they don't really matter. It's what happens later on down the line that really matters. But anyway, this is great. I overlooked that in the last class. Yeah. But at any rate, so this series here, 1 over square root of k plus 1 minus 1 over square root k plus 3, this is going to be the limit as n goes to infinity of all of this stuff. Oh, that's not going to fit, is it? So limit of all that stuff. If we look at it here, these two terms have a constant on top and something that's growing on the bottom. So this limit goes to 0, the limit there goes to 0. And so at the end of the day, this is 1 over root 2 plus 1 over 3. That is our limit of this function. Or sorry, our sum of this series. So it converges to, oh wow, that was a lot of writing. So it converges down to this. Okay, maybe I'll just zoom in on the end part here. A little hard to see. So, any questions about this one? This technique, by the way, is something we call a telescoping series. Or I should say, not technique, but this type of series is something called telescoping, which is kind of like the first term or two survive, the last term or two survive, but everything in the middle keeps canceling out as you go along the series. You would have seen that a lot better if I had used here k plus 2 instead of 3, but like I said, this was an interesting one all the same. Any question at all? We're good. All right. So that was the last long one. The rest of these are a little bit simpler. So let's look at number 4. We're looking at the series from 0 to infinity of 1/4 to the k. Right? We look at that one. Probably not a big surprise. This is geometric. Right? This basically fits exactly the bill for a geometric series, which I'll just remind you here. 0 to infinity, a times r to the k. Right? So that's the form of a geometric series. Here, a is 1, r is 1/4. The condition for a geometric series to converge is that absolute value of r needs to be less than 1, which in this case it is, so it converges. And so here we know that this sum is going to equal a over 1 minus r. A over 1 minus r. That's 1 over 3/4, which is 4/3. So geometric series are pretty easy to work with, which is fantastic. Right? It's one of the few types of sums we can add up, and it's one of the very few sums that are really easy to add up. Because we have a nice formula for it. Any questions about that one? Let's go ahead and look at the next one here. 5. All right. Here we have the series from 0 to infinity of -9 over 10 to the k. And probably not too very much surprised, this is again geometric. Right. And this one, a is 1, r is -9 over 10. Right? So r can be negative. There's certainly nothing wrong with r being negative, because when we check the absolute value, or sorry, when we check for convergence, we use the absolute value. So that negative kind of doesn't mean anything. Right? So the absolute value of that, by the way, is 9 over 10, which is less than 1. So we know that it converges. Right? And what does it converge to? Well, it's a over 1 minus r. A over 1 minus r. Right? So that's 1 over, right, that is 10 over 10 plus 9 over 10. And also assume you're better at arithmetic than I am, so you can probably figure out that's 10 over 19. So probably not too much of a problem. Any question there? So let's look at the next problem. 6. So here I have the sum from k equals 0 to infinity of 3 times -pi to the -k. So that looks really close to a geometric series. But is it one? And if so, how do I make it one? So it is geometric. How do we check that? Right? Because that minus k there, as it stands, that doesn't look very geometric. But if you remember, when we have two powers multiplied, say a to the p times q, that's a to the p to the q power. So I'm going to pull the negative one inside and leave the k on the outside. This is now geometric with a equals 3, r equals negative pi to the minus 1, which, by the way, is just negative 1 over pi. So absolute value of r is certainly less than 1. This converges. And so it converges to a over 1 minus r. A is 3 over 1 minus r, so 1 minus 1 over pi. The bottom, if you want to simplify this, would be pi plus 1 pi. Or you want to combine these two together. And then at the end of the day, this is 3 pi over pi plus 1. Yep. Nice quick geometric series there. Any question about that one? Great. So let's look at the last one here. Number 7, we're looking at the sum as k goes from 0 to infinity of 4 to the 2k over 12 to the k. Again, this looks pretty close to a geometric series, but is it one? The answer here is yes, this is a geometric series. We can use those same properties of exponents here to say, all right, well, I'm going to pull the kth power out of both of these. This will be 4 squared on top, 12 on the bottom, and then the k comes out like this. Right? Hopefully that seems good. And now I can expand all this stuff in here. So this is 16 over 12, k. Right? So this is in fact geometric. You're going to have geometric with a equals 1 and r equals 16 over 12. Okay. Now how about the absolute value of r? Well, that's 16 over 12, or 4/3 if you want to simplify it, which is bigger than 1. Well, really, we can say bigger than or equal to 1. So that means this diverges. Right? Because the ratio is too large. So this series doesn't converge to anything. Any questions there? So the geometric series stuff, I don't know. I quite enjoy it personally. It's not too bad. You can get some neat things out of it. And some of those neat things are like the examples in problem 2. So let's go ahead and get started with that. So problem 2, part 1, I want to ask, well, this repeating decimal here, what is this actually equal to? Right? So kind of know this is 2/3. You've seen this a lot. But why is that 2/3? Why does 6's repeating forever give you 2/3? Right? It kind of feels right, but how do you actually verify it? Right? Well, what we're going to do here is we want to take this repeating pattern and split it up into its individual pieces. So here, it's just the same number repeating over and over. So I'm going to write that as 0.6 plus 0.06 plus 0.006 plus 0.0006 and so on. Right? So I'm just chunking out each repetition in this decimal. And now what I'm going to do is I'm going to factor out that number that's being repeated. So here, it's a 6. And it's 6 times 0.1 plus 6 times 0.01 plus 6 times 0.001 plus 6 times 0.0001 and so on. Right? Okay. Now, you can rearrange this slightly if you want to get to the geometric series you're going to use quicker. I think this pattern, I kind of think this procedure makes more sense. It's at least easier to see. So I'm going to stick with this. So here, this is 0.01 to the first power. This is 0.01 to the second power. This is plus 6 times 0.1 to the third power, to the fourth power, so on. So once we're at this stage, we can see it's a geometric series. And so we can rewrite it as a geometric series. Now, as it stands, the pattern looks like this. Right? Since we have a 1 here, then a 2, then a 3, then a 4, this series starts from k equals 1 to infinity. Right? Because again, we're starting with the first power of something. Again, there's a way to rearrange it so you can start at 0, but I think, again, this is easier to wrap your head around. All right, so now that we're here, we need this to start at 0. So we're going to do that re-indexing trick from earlier. I'm going to take this sum, and I'm going to lower this number by 1. Technically, I lowered that infinity by 1 as well, but infinity minus 1 is kind of infinity. Right? And since I lowered this by 1, I have to raise this k over here by 1. Right? So I have that k plus 1. But again, I don't want a k plus 1 there. So what I'm going to do is use the fact that this is 0.1 times 0.1 to the kth power to say this is 0.06 times 0.1 kth power. Right? So I just took that extra copy of 0.1 that I had and put it over here on the 6. So now I got that. But now this is geometric with a is 0.6, r is 0.1. Of course, that's going to converge. And I have 0.6 over 1 minus 0.1. So that's 0.6 over 0.9. And I'll let you do, whatever you want to do to simplify this. A good idea would be to get rid of all the decimals, so multiply the top and bottom by 10. And once all the decimals are gone, you can simplify that, and here you'll see 2/3. So this is how you go about showing something like this is a fraction. You just turn it into a geometric series and go from there. Now, the same principle applies no matter what, no matter how many numbers are being repeated. So here it was just one number, but what if it's like a group of numbers that are being repeated? Right? The same principle applies. So here we had 0.037 r. Right? So this is 0.037, 037, 037. Well, what's going on here? Well, here I have 0.037 and then plus 3 zeros and then 0.037 plus 0.986 zeros and then 0.037 and so on. Right? So I get a pattern like this. Here, I'm going to say, all right, well, really the 0.037 is repeating, but if that's a leading 0, I can factor out a 37. And this is 0.001. Here, this is going to be 37 times 0.001 squared. Right? And this one will be 37 times 0.001 cubed. Right? So exact same procedure as last time, but now instead of 0.1 as the ratio, it's 0.001. Right? So it's just, this should have as many digits as the repeating part here. Probably pretty reasonable to expect that, I think. Right? So we get our geometric series as k equals 1 to infinity of 37 times 0.001 the k. And now we just do the same reindexing trick. Right? So I'm going to drop this by 1, and then I'm going to raise the other one by 1. And now that I have that, I need to get it to look like a normal geometric series. So pull out the extra 0.001. And you'll notice here, what we're going to get is 0.037 coming out. And then times 0.001 to the k. Right? That's not an accident. That should always happen there. And now, just go ahead and use our geometric series. So a over 1 minus r, so 0.037 over 1 minus 0.001. That'll be 0.037 over 0.999. Right? And again, we want to get rid of the decimals, so I'm going to multiply the top and the bottom by 1,000 here. And we'll see that's 37 over 990. And that's our decimal. So, great. So that's how we can take, strings that are more than one digit. We can have as many digits as we want in that string as long as it's repeating. We can always break it down into this kind of geometric series pattern. So there is 1 minute left. I do want to do this last problem, but of course, if you have somewhere to be, don't feel obligated to stick around. But I want to do this last problem, and I actually wrote the wrong thing in the notes. Or maybe I didn't, but I want to do a different one. I want to do the example 0.125, where just the 25 repeats. So 0.1, 25, 25, 25, so on. Right? Because this is something kind of interesting, where the repetition doesn't start right away. Now the technique's going to be very similar, except we'll see a little bit of a difference here. Right? So if the repetition doesn't start right away, what you want to do is split off the part that doesn't repeat from the part that does repeat. Right? So the first thing here is to, actually I can do that right here, write this as 0.1 plus 0.0252525. Right? Because that part that doesn't repeat, we're just going to sort of deal with that later. Okay. Now, the part that's repeating here, we're going to do the same thing we always do. Right? So here we have our 0.1 plus All right, so the part, let's see. Maybe we should write it like this, 025 plus 0.00025 plus 0.12525, and so on. Right? Now we'll do our usual thing here. 0.1 plus 25 times 0.001 plus 25 times 0.1241. Right. 5, this one will be 1, 2, 3, 4, 5, 6, 1. Right, so you to get what this decimal here should be is you count how many decimal places you have here and then write this thing with exactly the same number of decimal places. Right? Now here, this one I find easier to do by saying, all right, 0.001 is 0.1 to the third. Right? You just count however many decimals you have and it's 0.1 to that power. Right, next one is 25. This is 0.1. This has 5 decimal places. That's to the 5th power. And this is 25. This one has 7 decimal places. This is 0.1 to the 7. Right? Now you want to see the pattern that's going to show up here. And if you look at it, it's just odd numbers, right? So again, ignore that first bit. That's not really relevant here. Right? So here, let's say, I don't know, maybe we start this at so these are odd numbers. So let's start this at k equals 1 to infinity. And this is going to be 25 to the 0.1 2k plus 1. Right? 2k plus 1 gives us that odd number pattern that starts with 3. And now, we want to fix this to start at 0. So we're going to do our reindexing trick again. 0.1 plus the sum from 0 to infinity of 25. The 0.1. Now here's the tricky bit. Remember here, we're changing the k with k plus 1. So this is now 2 times k plus 1 plus 1. That's the important bit to keep in mind. And now it's just a matter of, getting this k by itself. So it has a couple extra steps compared to usual, but so this is 2k plus 3. Right? And what we're going to do is, right? So the plus 3 part, I'm going to break that off, much like I did with these ones up here. This had a, where were we? I guess either one would have been fine. But here, I took this plus 1, and I took that 0.1 and I multiplied it to the 6. Right? Down here, I have plus 3. So I'm going to take 0.1 to the 3rd power and multiply it by 25. At the end of the day, that's 0.025. Now here, then I will have, I'll do this in 2 steps here. So that takes care of that part. Right. To finish this off, this is 0.025. I need to square this number in here. So this is 0.01 to the k. Right? I just pull that square inside the parentheses. And now I have my geometric series set up. This is 0.1 plus a over 1 minus 0.01. Now I can get my fraction here. This is 0.1 plus 0.025 over 0.99. Okay. And now it's just a matter of, making everything a nice fraction. So 0.1 is 1 over 10. Here I need to multiply the top and the bottom by 1,000 to get rid of all the decimals. That's going to give me 25 over 990. And at the end of the day here, this is going to be 124 over 990. So give me 1 second. I'll be right back for any questions. All right. Oh. No questions. Thank you guys for watching. With that, hopefully that was kind of fun. Like I said, I really enjoy these geometric series problems and these decimal expansions in particular. I think they're quite fun. But with that, we'll call it there. Have a good afternoon, and I'll see you guys later. See you tomorrow. Good one.